Okay, this lesson should give you a little bit of an introduction to the normal distribution. So basically, we're just going to look at some of the properties of the normal distribution here today. And in the next lesson, we will look at how you can how can you use those properties to do some more in-depth calculations using the normal distribution. But hopefully by the end of the day, you will just sort of understand sort of the context around the calculations that we are going to be doing tomorrow. So we already know a little bit about the normal distribution. We've seen it in back when we did distributions back in section 1.2. So let's just sort of summarize what we learned back in that section. So we knew that the normal distribution, if we were to draw it, it roughly looked kind of like this. Okay, it had this mound shape or this bell-shaped sort of distribution, and in the center is the mean. Okay. So again, what did we learn? We called it the mound-shaped, or we called it a bell-shaped distribution. Um, we knew that you learned that the mean, the median, and the mode were all pretty much the same. And in a perfect normal distribution, they're all exactly the same, which means that any of the properties that apply to the median, let's say, also apply to the mean value as well. The data, of course, is symmetric about the mean. So we've got half of the distribution over here on the left-hand side, and half of the data appear over here on the right-hand side. So normally, that is a property of the median. The median is the value that splits your data set in two, but because our mean and our median are the same, our mean also splits our data in two for the normal distribution. Now, in this one here that I've drawn, the data are continuous. I've drawn a nice smooth curve, but we can also talk about a normal distribution where the data aren't continuous. And that's what we did back in unit 1.2, where we made those histograms. And we described the shape of the histogram as being having a normal shape, even though we had individual little bars on our histogram that weren't precisely continuous. Okay? So why do we care about the normal distribution? The normal distribution, it turns out, crops up a lot in sort of the everyday situations that we encounter. Most things that are actually physically measured will follow the normal distribution. And by following the normal distribution, what we mean is that if you've got, let's say we think about this as a graph in terms of frequency, and this is sort of our values across the bottom here. What we're going to end up with is a lot of things sort of in the middle. And then very few things at very large values, and then a few things down here at very, very small values. Okay? And it's sort of this pattern of very few things, then a lot of things close to the mean, and then a very small number of things at very large values is kind of what we mean by the normal distribution. So for some examples here, let's say you take 2 dice and you roll them, and then you add the numbers that show up on the 2 dice. And you do this like 200 times. And then you make a histogram of the sums that you get. Well, you can see that the general shape of this histogram here follows the normal distribution. Okay, you are much more likely to get a 7 or an 8 or a 6, or those numbers in the middle, than you are to roll a 2 or a 12, those numbers at the very, very end. Beside this, you can see a graph of female shoe sales. So again, if we draw a nice smooth curve around this, we get what looks like a normal distribution. What is this telling us? That if you look at the population of females who are buying shoes, most of them have average size feet. 7.5, 8, 8.5. There's a very small number of people that have size 4. There's a very small number of people that have size 14 or 13. Okay, most of the people are close to the mean. Okay, and things like heights here. This is a smooth curve of heights of 14-year-old girls, where most people have a height somewhere here in the middle. There's a very small number of very short people, a small number of very tall people. Most people are kind of there in the middle. Okay, and you're going to see this pattern when you for almost every physical situation you can think of. If you think of how far people can throw a baseball, some people can throw it really far, some people not very far. Most people are going to be somewhere in the middle. Okay, and this pattern also holds true if you're thinking about the errors or the uncertainties in determining something. So if you've done physics, you've probably done a lot of error propagation calculations or uncertainty calculations or things like that. If you think of measuring something repeated, a number of repeated times, most of the times you're going to get a value that's kind of close to the true value, but you're going to get a small number of values that are much, much larger and a small number of values that are smaller by a considerable amount. So errors or uncertainties are also normally distributed. Okay. Now, if we're describing a normal distribution, we describe it according to two parameters or two numbers. Okay. And we've already encountered these two quantities before. One of them is the mean, which we refer to as x bar. Okay, this of course is the center of the distribution, because it's a measure of central tendency. And we talk about the standard deviation, or sigma. And standard deviation, of course, is a measure of the width of the distribution. Okay, so the shape of a normal distribution always stays the same. Shapes are the same, okay, but its location can change if we change the mean, and its width can change if we change the standard deviation. So I've got a little graph here showing the three normal distributions. Okay? So first, they're just labeled A, B, and C. So A is the light blue one, B is the dark blue one, and C is the red one here. If we look at A and B, maybe I should do this in a different color. Let's do A and B. These two have the same mean value. Okay, it's been placed at 0. So x bar is the same. Okay. What is different about the two of them? Well, they have different standard deviations. So the width of the distributions is different. If, on the other hand, we look at A and C, okay, so let's do this in, I don't know, let's do blue here. A and C, these two have the same standard deviation. Okay, so the two curves have the same width to them. The only difference between them is one is shifted over, and it's shifted over because they have different means, or different standard deviations. Okay, sorry, different means, not different standard deviations. Different mean. Okay. Okay. So changing the mean shifts the curve to the left or right. Shape stays the same. Changing the standard deviation makes it wider or it makes it narrower, but in general, the that pattern that we see with the normal distribution stays the same. Okay? And because that pattern stays the same, we can talk very specifically about how much of the data is in each section of a normal distribution curve. Okay, so this is where things start to get a little bit mathematical. Okay? So usually when we have a normal distribution, we talk about the area underneath the curve, or all of the data sort of fits underneath the curve, because the height of the curve at each point represents the number of data points at each of those values. So the area under the curve is 1, or 100% of the data falls underneath this nice smooth curve here. We can divide this into regions here by the number of standard deviations away from the mean a certain value is. So our mean value is right here in the middle. Okay, if we go over one standard deviation, we're coming to whatever the mean is plus one standard deviation. So this is mean plus standard deviation. So if the standard deviation was, if our mean here was 0 and our standard deviation was 6, this would be a value of 6. Or we can go to the mean minus 1 standard deviation. So if our, again, our standard deviation was 6, this would be like a value of minus 6. Okay? And then we can look at how much of the data is contained in these regions here. Okay? Between the mean and the mean plus 1 standard deviation and the mean minus 1 standard deviation. So each of those two sort of shaded red areas have the same amount of data because it's symmetric on the curve is symmetric around the mean, so they both have the same amount. Each one contains about 34% of the data. So we often say that 68% of the data is within 1 standard deviation of the mean. Okay, and this is true for any normal distribution curve that you have. The mean can be different, the standard deviation can be different, but that region in the middle from minus 1 standard deviation to plus 1 standard deviation is always going to contain about 68% of the data. Okay? And we can sort of continue this on. In the next little section, okay, we go from 1 standard deviation here out to 2 standard deviations. So this would be the mean plus 2 sigma. Okay? And down here it would be the mean minus 2 sigma. So if we look at each of these two blue shaded regions, you can see from the graph there that each one contains about 13.5% or 13.6% of the data. Okay? Again, it's symmetric on either side. So in total, from here to here, so this region that is within 2 standard deviations of the mean, we have 95% of the data. And we can keep doing this further and further, okay? If we go out to 3 standard deviations, within 3 standard deviations of the mean, we have 99% of the data, actually more than 99, about 99.5% of the data. Okay. Okay. So in each of these sort of regions of the curve, okay, there's always going to be a certain percentage of the data. Okay. And it's the fact that there's always a certain percentage of the data in these certain regions is what lets us do these calculations with the normal distribution. Okay? So we're going to get more into these kinds of calculations in the next lesson, okay? But we'll do some fairly basic ones here today just so you kind of get the idea, okay? All right. So here's an example of the kind of question we can answer using the normal distribution. At a high school, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6 centimeters. If there are 800 boys at the school, how many will be between the heights of 168 and 180 centimeters tall? Okay. So it's helpful in all of these questions to draw yourself a normal distribution. And we're going to use one here that has all of these percentages on it just to help us out here. So here we've got our normal distribution curve. We know that the mean is 174 centimeters. Okay. The standard deviation is 6 centimeters. So from the mean out to plus 1 standard deviation is 6 centimeters. And the other way is 6 centimeters as well. Okay, so what that tells us is this value here that is plus 1 standard deviation is going to be 174 plus 6, so 180 centimeters. And this would be 174 minus 6 is going to be 168 centimeters. Okay? And it just so happens that what they're asking us here is how many will be between 168 and 180. So how many are in this region here, okay, or this shaded area from +1 standard deviation to -1 standard deviation. Okay? Well, we know that this is going to contain, I'm going to use the numbers that are right on here. So 34.13 and 34.13 is a total of 68.26% of the data is in that shaded area. So what we want here is 68.26% of those 800 boys are going to have a height in that range from 168 to 180. So 0.6826, just change that percent into a decimal, multiply by 800, and we get 546.08. So we expect, if these heights are in fact normally distributed, we expect, let's round it off here, 546 boys in that height range. So we're just using the fact that between +1 standard deviation and -1 standard deviation from the mean, we expect 68% of the data points to be in that region. Okay. And so this format is kind of what we're going to follow even tomorrow when we do more complicated calculations. We're going to sketch out our normal curve. We're going to shade in the area on the normal curve that we want to find, labeling it with the key values. So we labeled ours with the mean and then the range of values that we wanted to find. And then we're going to work out our percentages. So let's do one more here, just so everybody has the idea. Same high school. Boys' heights are normally distributed with a mean of 174 centimeters, standard deviation of 6 centimeters. Slightly different question. Still 800 boys at the school. How many will be over 186 centimeters tall? So again, we've drawn out our normal curve here. Let's label it so we know that our mean is 174. The value that we're interested in, we know the standard deviation is 6. So we know that this is going to be 6 out here. We know that from here to here is going to be 6 as well. From here to here is going to be 6 as well, because each of those bars is separated by 1 standard deviation. So 1 standard deviation above the mean is, again, 180. 2 standard deviations, we add on another 6. That gets us 186. So we want the number of boys that are over 186 centimeters tall. So we want, like the people who are over 186 centimeters tall are in this region of the graph here. They're more than 2 standard deviations above the mean in terms of height. Okay, so what percentage of people are in that shaded region? Well, it probably is easier to calculate the percentage of people in the unshaded region. So I'm going to think about this first. What percentage of the data is in the unshaded region? Okay, well, we know that in this entire half of the data from the mean to the left is 50% of the data because our normal distribution is symmetric. So we've got half of it in this region from, to the left of the mean. Okay. And then if we look, we've got two other unshaded regions here and here. Okay, we know that from 174 to 180, or for the mean up to +1 standard deviation, we have 34.13% of the data. And then in the next region, from one standard deviation up to 2 standard deviations above the mean, we have 13.59% of the data. So our entire unshaded region here is 97. What is this? 97.72% of the data. So our shaded region then is going to be 100 minus that 97.72, or 2.28%. So 2.28% of the data is in that shaded region. What does that mean in terms of the number of boys at this high school? Well, we want 0.228% of 800 is going to give us 18.24. So out of the 800 boys in this school, we expect 18 boys with a height over 186.